गुड इवनिंग सर।
यस, गुड इवनिंग विश्वास। तो कब जा रहे हैं आप? कल?
यस सर।
यस, हमारा कोऑर्डिनेशन पार्ट लेफ्ट बचा हुआ था। और उसके बाद
यस सर।
हमारा ऑर्गेनिक स्पेक्ट्रा। यस ना?
यस सर।
ये लेट बी स्टार्ट इन द लेफ्ट पार्ट ऑफ कोऑर्डिनेशन। लास्ट डे हम डिस्कस कर रहे
यस
थे
सर।
कलर एंड इलेक्ट्रॉनिक स्पेक्ट्रा। यस ना?
यस सर।
उसमें कुछ डिस्कस हुआ था?
यस सर, उसमें इतना हुआ था, लेपोर्टे सिलेक्शन रूल और स्पिन सिलेक्शन रूल क्या था।
यस यस। ये नेक्स्ट मूव ऑन इन कलर इलेक्ट्रॉनिक स्पेक्ट्रा। यस। What is organ diagrams in color and electronic spectra? What the difference between organ and Tegano-Segano diagram? What the applications
यस।
used in coordination?
यस।
Explain.
सो सर, orbital diagrams are the correlation diagrams which are used to explain the spectra of any any coordinate complex or any coordination compound. For example, sir, let us say we have titanium H2O6 3 positive. It is the number of electrons in d subshell is 1. So it is expected that the number of transition would be 1, but in the actual spectra, the number of transitions are not 1, but instead there are 2 transitions or 2 peaks were observed. So the to correlate the number of transition that were obtained in the actual spectra of the coordination compound, orbital diagrams are used. Orbital diagrams are used, sir, only for high spin complexes, only for high spin complexes. And sir, but the Tanabe-Sunabe diagram or TS diagram can be used for high spin complexes as well as low spin complexes. Both are the both are correlation diagrams, and both are not the actual spectra, but are used to explain the number of the transitions with the real spectra.
Yes.
This is for high spin allowed complexes. Orbital diagram is limited to high spin and spin allowed complexes. Tanabe-Sunabe diagram can be used for high spin, low spin, or spin allowed, spin forbidden, every kind of complex.
Yes, good. Any drawback and limitation of organ diagram and Tegano-Segano diagram?
The major limitation of orbital diagram is that, sir, it is applicable only to spin allowed and high spin complexes. So those complexes in which are spin forbidden or which are low spin complexes, we cannot use orbital diagrams to explain their spectra. And sir, the one limitation of Tanabe-Sunabe diagram is that, sir, it is very complex to analyze. The complexation of the TS diagram uh, is one limitation of Tanabe-Sunabe diagram.
Yes, good. What the difference between DD transition and chart transfer spectra in coordination?
Yes. Yes. So the D transitions are those transitions in which mainly the metal ion which is under our observation is used only. For example, if the transition between the two energy levels of the d orbital takes place, then it will be a dd transition. But if along with metal, ligand also takes part in the transition. For example, the transfer of electron from ligand to metal takes place, or from metal to ligand takes place. From ligand to metal takes place, or metal to ligand takes place, or sometimes it may be possible that the transition is between two two metals which can be same or different. So if instead of d orbitals we use instead of d orbitals, the electron is transferred from the p shell of p orbital of metal to the empty d of the p of the ligand to empty d of the metal, or from the metal to the sigma star or pi star of the ligand. If the transfer of electron takes place in these ways, then the spectra would be known as charge transfer spectra. And sir, generally, it is observed that the charge transfer spectra are more intense, or sometimes it may be possible that compound which is having charge transfer spectra is colorless, because because for that compound what may happen is that the value of the energy increases, so its wavelength decreases from the range of visible radiations, so color of that particular complex would not be visible. But if we consider dd transitions, then generally color would be observed, but that color would be very less intense. So these are the major differences, sir, between the dd transitions and charge transfer spectra.
Yes. Yes, some words used in organ diagrams. Rega
Some,
parameter
yes, sir.
and Nevelski
Mm-hmm.
effect. What the uses and
Yes.
application of these words?
So we have two parameters, sir. One is Reka parameter and second one is Nafe-Lexotic effect. So Reka parameter is the parameter which defines the expansion of the electron cloud around a metal ion. If we have an free metal ion, the electron clouds of the orbital would repel each other. But if there are ligands attached to the metal ion, then the electron cloud of the orbitals of that metal ion would feel some relaxations, and those relaxations are defined in terms of Reka parameters, sir.
Is what the formula?
Formula of Reka parameter. Sorry, sir, at this moment, I'm not able to recall the formula of the Reka parameter.
What is Nepalski series? What is Nepalski series?
Yes, sir. So it is, sir, this series defines the effect of the ligands. This is define the effect of the ligands such that how much a ligand would cause relaxations in the repulsions among the various electron clouds. So series which defines as, for example, sir, if we have two ligands X and Y, so and ligand Y generates more relaxations in the electron cloud of the metal, then the Nephel exotic effect of Y would be more than X, and series would be like this. X has less effect than Y. So a series is formed depending on the orbitals, and that particular series is Nephel exotic series. And as far as I can remember, such series is the some of the elements of the series are like this: F negative, OH negative, Cl, I negative.
Yes, good. And next move on. Magnetism. Yes. What is magnetism?
Yes.
How many types of magnetism? What's the difference between para-di, ferro, ferri, entoferromagnetic? Explain.
Yes. So magnetism is mainly of two types: paramagnetic and diamagnetic. If we have if unpaired electrons are present, then that particular type of magnetism will be paramagnetism, and if no unpaired electrons are present, then the magnetism would be then the substance would be diamagnetic substance. If non-paired electron, then diamagnetic. If unpaired electrons, then paramagnetic. Other types of other type of magnetism can be ferromagnetism, antiferromagnetism, and ferrimagnetism. So in the absence of the external field, the kernels which are present in any molecule are randomly oriented. But if we apply any external field, and in presence of that particular field, if the kernels arrange themselves in any particular direction, in any particular fixed direction, then in such case the magnetism of that complex, or the magnetic nature of that complex, increases by a very high value, and that complex is known as ferromagnetic complex. Similarly, if in the presence of external magnetic field, the kernels of the molecule arrange themselves in such a way that they cancel out each other's effect, then the molecule will appear to be as a paramagnetic substance, but actually will be a diamagnetic substance, as the effect of the kernels would be cancelled out by each other, and the magnetic and such type of substance are antiferromagnetic. And if in the presence of external magnetic fields, the kernels arrange themselves randomly or are in randomly oriented direction, then then the magnetism of that complex would increase, but up to a particular limit. In case of ferromagnetic substances, the magnetic nature of the substance increases by a very high value, but in case of ferrimagnetic substance, the increase in the magnetic moment would not be that much. So these are the main types of the magnetism, sir.
Yes, what is molar susceptibility and paramagnetic susceptibility and dimagnetic susceptibility? What the difference?
Mm, yes, sir. So if we plot a graph between the applied field and induced field, then in case of paramagnetic substance, the graph will look like this, is a straight line. Answer, if it is defined by xp is equal to mu mu effective square into Avogadro number upon 3RT. So this is the paramagnetic susceptibility and its formula. And if the graph is for diamagnetic, then induced field and applied field graph is like this, decreasing graph.
Yes. What is Curie law? Curie law and nil temperature, what the difference?
Yes, sir. So from this equation, we can see that xp is inversely proportional to temperature. Xp is inversely proportional to temperature. So, sir, above a particular temperature, if we plot the graph between temperature and magnetic value. So, above a particular, the graph for the xp and 1 by t, the graph will be like this. Above a particular temperature, all the substances are paramagnetic, but but Curie temperature is that temperature below which the substance is ferromagnetic. So below Curie temperature, the magnetism of the substance would increase rapidly. So Curie temperature is that temperature, sir, above which the substance is ferromagnetic, and above which the substance is paramagnetic, and below which the substance is ferromagnetic.
Yes, good. What is magnetic moment? How to determine magnetic moment in coordination? What the formula?
Yes. Yes. So, so magnetic moment is, if we talk about spin only, if we take the contribution of the spin only magnetic moment, then the formula would be n into n plus 2, where are the number of unpaired electrons. And if we consider total magnetic moment, that is, the contribution is due to spin only magnetic moment, and along with it orbital contribution is also present, then the formula would be n into n plus 2 into plus l into l plus 1. And sir, in case of complexes, the mu effective is given by g J into J plus 1 under the root, where G is a constant whose value is equal to 3 by 2 plus S into S plus 1 minus L into L plus 1 upon 2J into J plus 1. And the value of S, L and J can be determined from the term of that particular complex. So these are the major formulas of magnetic moment, sir.
Yes, what the formula for D block elements and transition element and F block, lanthanide and actinide? What the formula for magnetic
Sir,
moment?
this is the for lanthanide and actinides or F block element. The major formula used is mu effective is equal to J into J plus 1, where G is a constant whose value is given by G is equal to 3 by 2 plus S into S plus 1 minus L into L plus 1 divided by 2J into J plus 1. So this is mainly used for the F block elements. This formula is mainly used for the F block elements or some type of or the lower coordination complexes. And another formula which is used in D block, which is used for D block complexes, is mu effective is equal to N into L plus N plus 2 plus L into L plus 1, where N is the number of unpaired electrons, and this can also be written as 4s into S plus 1 plus L into L plus 1 under the root.
Yes, good. Yes, how many factors affecting to magnetic moment?
Yes, sir. So the one factor affecting magnetic moment is the number of unpaired electron present. Number of unpaired electron present. More will be the number of unpaired electron present, more will be its magnetic moment. Another factor is, sir, orbital contribution in magnetic moment. Orbital contribution is magnetic moment. Sometimes it may be possible that the complex doesn't have any unpaired electron, yet it shows magnetic moment. So that magnetic moment is due to its orbital contribution. So right now I can recall only these two main factors, sir.
Yes,
And
how many
the
types
third
of
factor,
magnetic moment, change in magnetic moment in coordination? How many types?
types of change in magnetic moment.
Yes.
Hmm. Sorry, sir. At this moment, I'm not able to recall the types of change in magnetic moment.
Yes, magnetic moment, simple is formula. Yes, you have already explained. Other one is ground state term change.
Yes, sir.
Regenerate. Yes, number 1 point. Orbital contributions. Yes, no, 1 point. Second point is first
Yes, sir.
perturbation theory. First perturbation theory is also changed.
First,
Yes, perturbation theory. Yes, perturbations. Second, third is a spin crossover. Spin crossover is also changes magnetic moment. Low spin to high, high to low.
Yes,
Yes.
sir. Hmm. LS coupling, I think so. The LS coupling also affect the value of the spin.
Yes, LS coupling. Yes. LS coupling, yeah, ground state orbital contributions. Yes. Free ions coupling, LS coupling. Yes. 5 factors. Yes, no. 6 factor.
Okay, sir. These are the 5 factors which affect the value of the magnetic moment.
Yes.
Okay, sir.
Yeah, next move on. Stability of complex and reaction mechanism in coordinations. So first of all,
Yes.
what the any reactions is affect by the thermodynamical stability, chemical kinetically stability? How to measure? Which
Yes,
one
sir.
is kinetically stable and which one is thermodynamically stable? What the procedure and method from your side?
Uh, yes, sir. So, first of all, before measuring kinetic stability or thermodynamic stability, we need to find out which kind of mechanism do the complex follows. Whether it follows the dissociative mechanism, or it follows the associative mechanism, or it follows the interchange mechanism. So these are the main types of mechanism which are involved in the coordination reaction mechanism. If the rate of the reaction depends only on the concentration of the substrate, then that particular mechanism is dissociative mechanism, and this mechanism is mainly followed in octahedral complexes. If the rate of reaction depends on the concentration of substrate, and also on the depends on the concentration of the substrate, and also on the concentration of substrate, and also on the attacking species. Then this kind of mechanism is associative mechanism. Dissociative mechanism is like, sir, we can say SN1 limiting mechanism, also known as SN1 limiting mechanism, and associative mechanism is SN2 limiting mechanism. The Now, if we talk about the thermodynamic stability and kinetic stability, so these two factors are independent of each other, and these are not interrelated. It is possible that, sir, a compound is thermodynamically stable and it is kinetically reactive. It may be possible, sir. For example, if any compound has Joule-Thomson distortions, JTD, then there will be axial elongations or axial compressions. As we know, due to JTD, there will be relaxations, and the energy of the compound would decrease. So thermodynamically, that compound would be more stable. But due to increase in the size, or due to axial elongation, the two bonds of that particular compound, mm, of that particular compound or of that particular complex would become weak. So uh, due to the weakening of that bonds, the compound will become kinetically labile. So the thermodynamic stability and kinetic lability are independent concepts, and they are not interdependent on each other. If the compound is labile or reacts very easily, then that would be kinetically labile compound. and if it is thermodynamically less stable or thermodynamically more stable, that would be determined by its thermodynamic stability. So these are the main things, sir, about the thermodynamic stability and kinetic stability.
Yes, what is Irwin-Williams series?
Yes, sir. Irving-Williamson series is used to explain the thermodynamic stability of some of the metal ions, and according to Irving-Williamson series, mm, it looks like barium 2 positive would be thermodynamically less stable than Sr2 positive, calcium 2 positive, iron, cobalt, nickel, copper, zinc. This is Irving-Williamson series, sir.
What the application of Irwin-Williams series?
Sir, Irving-Williamson series is mainly used to determine the thermodynamic stability of the complexes. If the complex is formed from the starting of the metal ions, then it would be thermodynamically less stable, and if the complex is from the ending of the series, then that would be thermodynamically more stable. And one more thing, Irving-Williamson series tells us about is that the complex of the copper 2 positive ion would be more stable than the zinc 2, thermodynamically more stable than zinc 2 positive ion.
Yes, what's the difference between labile and inert complex? Any example?
Yes, sir. So labile complexes are those complexes whose reactivity is high, and inert complexes are those complexes whose reactivity is low. So labile complexes are generally high spin complexes. High spin complexes are labile complexes. Their labile complexes. The CFSC value of labile complexes would be low, and inert complexes are those complexes uh, which are highly stable and have high value of CFSC. So those complexes are inert complexes, and this concept of lability and inertness is mainly applicable to octahedral complexes of 3D series. If we consider the case of square planar complexes, generally all the square planar complexes are labile complexes, and mainly 4D and 5D series elements are also labile. So if we have any compound which have D3 configuration, for example, vanadium H2O6 2 positive, then it as it has a high value of CFSE, so it will be a inert complex. For example, cobalt H2O6 3 positive, D6 configuration, low spin, inert complex. This is also an inert complex, sir. And if we consider the example of iron 3 positive, it is an high spin complex, so it is labile complex. These are some of the some examples of inert complexes and labile complexes.
Yes, good. Next, move on trans effect. What is trans effect? What the main application of trans effect?
Yes, sir. So, if we have any square planar complex, and if we have any square planar complex LL. So to understand the reactivity of the square planar complex, we need to study the trans effect. Any incoming ligand, let us say, is IL is the incoming ligand. So incoming ligand will attack on the square planar complex and affects its geometry. So the reactivity of the square planar complex will depends on the incoming ligand, and the which of the ligand would be removed from the complex, from the square planar complex, is determined by its trans effect value. So the complex which has high trans effect value, so the ligand which has high trans effects value, the uh, it will be more clear with an example, sir. Let us say this is an example. This is a square planar complex. Now incoming a ligand is coming. So which of the four ligands which are already present on the square planar complex would be removed, and so that the incoming ligand can get attached to it. So the removal of the ligand from the square planar complex is determined by trans effect. So trans effect is a series which helps us in understanding.
Yes, carry on.
Yes, sir. And the so the ligand which is coming has to perform mainly two functions, as will be attached to the metal ion complex. So the electron density on the metal would increase. So the incoming ligand, or the ligand which will be attached to the metal ion, should be a good pi acceptor, so that the electron density on the metal ion would not be in excess. Apart from this, sir, it would be a good sigma donor, so that it may increase the electron density on the metal ion, and and the ligand which is to be removed can be removed easily. So there are two main function of this incoming ligand. First, it will act as an pi acceptor ligand to stabilize the compound, and then as a sigma donor ligand. Then as a sigma donor to increase the reactivity of the metal ion by removing one of the ligands from the metal complex. So generally the trans-directing series looks like this: CO, Cn negative, H. First is which are good pi acceptor, then good sigma donor, which are good donors,